Okay. All right, so here we have a summary of the system. We have a torque being applied to this load. The torque is proportional to the current. Alpha is just a constant. There is friction between the shaft and the bearings, and the load has an inertia J. So let's start by modeling the system. And let's assume, for example, that this is the load. If you look from this side here, we have a torque being applied to it. This torque is alpha times I of t. And there is friction. Friction will act against the input torque, against the speed of this shaft. And what is the magnitude of the torque applied by friction? It's the coefficient of viscous friction times what? Times position, speed, acceleration.
Would it be the rotational velocity?
Exactly, it would be the rotational velocity or the angular speed. You're going to call it here omega t. Assuming now that these are all the forces acting here and we are driving a load. So we can say that anything that rotates in that direction is positive because that goes along the shaft, the input torque. So we have the input torque alpha I of t minus the coefficient of viscous friction times the speed equals to the moment of inertia times the acceleration of that thing. And the acceleration is nothing else than the derivative of the speed. So omega t dot. I can rearrange this equation, j omega t dot plus b omega of t equals to the input torque, which is a constant times the current. We want to find the impulse response, so we can now take the Laplace transform of this. So let's do that. What is the Laplace transform of j? Laplace transform of j is j. What is the Laplace transform of omega dot? What is the Laplace transform of omega dot, or the derivative of something? The derivative becomes s and times the Laplace transform of omega, which in this case here is omega s. S times omega s. So the derivative of omega, right? Same as here. Minus the initial speed, which would be omega 0. In this case is 0, but let's put it there because we can't forget it. Plus b, omega of t becomes omega of s, and equals to alpha is alpha, I of t becomes I of s. We are saying that there are no initial conditions, so this is 0, but it wouldn't be if the system was rotating when we apply the torque. And you can now rearrange this expression. So on this side of the equation, you can keep everything with omega. That would be omega s times js plus b. And on the other side of the equation, we simply have alpha I of s. You can now create an expression for the speed, which is alpha times I of s divided by js plus b. Any questions so far?
Just could you quickly go over how you got the equation for the rotation?
This equation over here?
Yeah, just very quickly.
All right. So thinking about the system as a rotational system, so you're just looking at this shaft from this angle. It's just a circle. The torque is being applied in one direction here. The torque, the problem states that it's proportional to the current. So this is the input torque. Is driving the load that way. So the problem also states that there is friction between the bearings and the shaft. Friction always opposes direction. So logically, if this is applying a torque that way, the system will rotate that way counterclockwise. So friction needs to apply a force opposing that, so it's going to go clockwise. Friction is always the coefficient of viscous friction times the speed. Here we are dealing with a rotational system, so instead of using the linear speed, we're using the angular speed. So angular speed times viscous friction coefficient will give us the torque due to friction. Now, in a translational system, we know that the sum of all forces equals to ma, mass times acceleration. In a rotational system, we know that the sum of all forces, which is the left side of the equation, equals to the moment of inertia j instead of mass, because not need to take into account the geometry of this, times the acceleration. And the acceleration can be expressed as the first derivative of speed. Why speed? Because you're dealing with speed here. Right? This is speed times b. So we can only have one variable as a function of speed. This is simply omega dot, first derivative of speed, angular acceleration. And then this is the rearrangement of that equation. Is anything in specifically that you would like me to go over?
No, that was it. I got it.
Okay. All right. So then this is the Laplace transform of this equation. Are we good up to this point? Yeah. Okay. Now the first question says, calculate the speed response of the load to an impulse current, or the impulse response of the system, in other words. For an impulse response, then the current input is simply the function delta of t, Dirac impulse function, which when you take the Laplace transform is simply, if you go to the table, that would be, I don't think it's even in the table, is it? The Laplace transform of, should be in the table, let me just double check. Is the most, so it's the basic function, I think it's not in here. Yeah, I don't think it is on our table, but I'll tell you what it is. Yeah, no, it's not on the table. Okay. So it's not on the table, but the Laplace transform of an impulse function is simply 1. We can now rewrite this here as omega of s equals to alpha times, this is 1. And here we have j times s. If you look at the table of Laplace transform, we always have s here multiplied by 1. So let me divide the whole thing by j. Divide the whole thing by j, or just factor out j. Let's put it that way. Let's just factor out j here. We have s plus b over j. Nice. If I multiply this back in, it will go back here. Now we can find the speed of the motor, or the time response for an impulse excitation, that is omega of t. And omega of t is the inverse of this, which is exponential of, this is a negative b over j times t. Now, what is this inverse? What does this represent? That's the impulse response. But what does that mean? Well, the impulse response is based on the assumption that at time 0, we have a delta function that tends to infinity that is applied to the system and removed immediately after. So you can think about this as applying a very large amount of torque to the system at a very small amount of time and then let it go from there. Or just basically slapping the system, let it move, and then remove any excitation and see what happens to it. That would be the impulse response. Remember from lecture 2, when you talked about matches, we would light up a match and then the amount of smoke would decrease over time. That would be its impulse response. And the same here, we're now kind of slapping this mass, letting it rotate and then eventually decay to 0. Right? So we can see this as the impulse response of the system. It starts at a given value and then it slowly decays to 0. So if you plot this, we'll get exactly an exponential like the one we just did in the previous example, an exponential that starts at, in this case, when time is 0. It starts at alpha over j and then decays to 0 at time tends to infinity. This is the impulse response of the system to a current input, or to a torque input. Okay. Are there any questions here? No? All right. If there are no questions, I'll move on. The next question now asks us to find the impulse, the step response of the system. Now, instead of giving this current at time 0 and removing it, we are giving a current at time 0 and then holding that current constant. And it says a unit step input, so that means the magnitude of the current is 1, but it's a step input now. So let me see what I can. Okay, so let me just write. Let me just write here. This is the impulse response alpha over j 1 over s plus b over j. And that's the impulse response. Okay, so now we can move on, but now the current is given as a step. So the input here will change, and this will also change. If the current is a step input of magnitude 1, this is simply u of t. It's a current that will be turned on at time 0 and then held constant at 1 amp as time goes to infinity. What is its Laplace transform? What is the Laplace transform of a step function?
1 over s.
1 over s. Very good. 1 over s. So now when you replace I of s here, first we did 1. Now we are multiplying this by 1 over s. Right? That's I of s, 1 over s. And before it was 1. Okay. Now, this is now the step response of the system. We can find the inverse Laplace. To do that, we'll need to find the partial fraction decomposition here. Should I do the partial fraction decomposition, or are we okay? That's a good exercise. We can try it there. We can call this entire function here, or maybe just that function. Yeah, but we can just call this part here p of s, and we want to write, oh, excuse me, we're including that one. And now you want to write that because you have s that multiplies this. We won't find that in the table of Laplace transform. So we need p of s to be written as a over s plus b over s plus b over j. How do we find these coefficients? Give me the expression for a. A is p of s times what? Times p of s times whatever divides a, which is s evaluated at s equals to 0. Whatever makes the denominator here is 0. And this is equal to j over b. Right, this s will cancel that s. This s is 0, so 1 over b over j is j over b. And for the value of b, we have p of s now multiplied by this part here, s plus b over j. And this is evaluated at s equals to negative b over j, so that this part is 0. And if we do this, we are left with 1 over s. S evaluated at b over j is negative j over b. So those are the values for A and B. J over B, negative B, J over B. Okay. Any questions here? Can I erase this part? Well, if I hear no questions, I'll do it. Now this is the partial fraction. Now we have two terms here. B and J and minus J. Okay. Okay. So now omega of S is alpha over J divided by J over B times 1 over S minus J over B over 1 over S plus B over J. What is omega of T? The inverse Laplace of that. We can factor out this J's here. You see that they cancel out with this one in front. So we have alpha over B Laplace transform, inverse Laplace transform of 1 over S is 1. Inverse Laplace transform of this is exponential of negative B over J times T. That's now the speed of the motor as the motor is turned on and left to stabilize. We can plot this. And if we plot that, what do we get? We have something that starts at 0, right? When time is 0, this is 0. So excuse me, this is 0, so exponential of 0 is 1, 1 minus 1 is 0. It starts at 0. And when time tends to infinity, this here goes to 0, negative exponential of negative infinity. We are left with alpha over B. So the speed follows a curve like that. Okay. Now, before I move on, are there any questions here? No? All right. Now notice something interesting. First, we determine the impulse response of the system. Here it is. That's the impulse response of the system. This is the Laplace transform of its impulse. Over here, we calculated something new. We calculated the step response of the system. That is, we took the input, there was an impulse, we replaced that with a step. And how did you calculate the step response of the system? Well, we'll multiply the input by exactly the step response. Isn't this the step, the impulse response? We multiply the input by the impulse response, and we did the inverse Laplace transform of that. Didn't we just take the convolution of these two signals? Yes, we did, because we multiplied these two signals. And in the last example, the Laplace transform of the convolution of the two signals was simply their multiplication. So what it did here was exactly what it did in the last example. That exponential that was decaying to 0 represented the impulse response of a given system. And then you multiply that impulse, then you took the convolution between that function and an arbitrary input, which in that case was just a function that would start at 3, go to 1, and at 5 seconds would turn off. We took, by multiplying their Laplace transforms over there, we took their convolution. So we took the most elementary way the system can respond to an input, which is its impulse response. We took the convolution of that signal with an input signal, and through that operation, we now found the time response of the system for that specific input based on how it responds to an impulse. That's exactly what we did here. when you multiply this part of the equation by 1 over s, this is exactly the impulse response of the system. Here it is, that's the impulse. And you multiply that 1 over s to find its step input. This multiplication, if you go back to time domain, this multiplication corresponds to the convolution of the impulse, or convolution of this function, and the convolution of that function. So you're taking the convolution of the impulse response with the arbitrary input of the system. That's exactly what we did before. And by simply multiplying these two things, we are taking the convolution of them. Right? So you could have solved this using a graphic approach as well. Any questions? Any questions? No? Okay. There are no questions. Let's move on. Next question asks for the initial and final value of the load speed for a step current input. The final and initial value of the load speed for a step input. So basically, it's asking where does the motor start? Well, at 0. And where does the speed end? Well, it ends at alpha over b. Well, this kind of answers the question, but we had to take the inverse Laplace transform and plot the result to see. Instead, let's use one property of the Laplace transform that will help us solve this without even bothering with the output, the time domain. We can simply go back to this equation here and use a property of the Laplace transform that will allow us to figure out what these values are without computing the inverse Laplace. And this is the final and initial value theorem. You want to know which speed the motor starts and what speed it settles at. So the initial value, or the speed at which the motor starts, we can do all we did here. We would find 0. I just make time equal to 0 in the equation we found earlier, and you get this. But this is the same as saying, so the speed at time 0 is the same as the limit when s tends to infinity of s times omega of s. This is a property of the Laplace transform that we can use. We briefly went through this in the last lecture. Didn't really spend much time there. But this property was a very useful property because we can now look at where the system starts without even computing the inverse Laplace transform. We can solve for this. We can simply take the signal of interest, which in this case happens to be the speed, multiply that by s, and take the limit when s tends to 0, to infinity. So omega at time 0 will be the limit when s tends to 0 of s times that. So this s and that s cancel out. So I left with alpha over omega, 1 over s plus b over j. And the result of this, when s tends to infinity, excuse me, I wrote 0 here, should be infinity, is 0. We found the same value, but we didn't have to compute the inverse Laplace transform. Now to find the final value here, or at which point the maximum speed reaches, or the speed reaches as whether it settles, we can use the final value theorem. Or we could use the equation we had here just to make time tend to infinity, and we would find alpha over b. In the Laplace domain, however, that's equivalent to saying that omega at infinity, or as time tends to infinity, is the limit when s now tends to 0 of the same operation, s times the function of interest. This will now give the final value of the system. We can easily replace the expression for the speed here. This s and that s will cancel out. We now have alpha over j divided by 1 over s plus b over j. When s tends to 0, When s tends to 0, we are left with alpha over j times 1 over b times j. So j goes upstairs. They cancel out and I have alpha over b. Exactly what I had there. Right? So this way we can find this final value without even bothering with the inverse Laplace transform.